Hi, how are you?
Okay, so we'll continue with a set of beautiful pedagogical lectures on F-theory, and Timo will tell us now about matter and couplings in F-theory.
I hope so. Good morning, welcome back. So just a brief reminder, last time we discussed that the singularities in codimension 1 on an elliptic fibration can be resolved if they are in Kodara's list, otherwise no such resolution is possible to a flat elliptic fibration. This proceeds by including P1s in the fiber, resolution P1s, which then, by fibering them over the discriminant component, also give rise to new divisors. The divisors are in one-to-one correspondence with the Cartan U1 generators of the Lie algebra. The resolution curves themselves are in one-to-one correspondence with the simple roots of the algebra. And the volume of these resolution curves are the classical Coulomb branch parameters in the dual M theory. The F-theory limit consists in taking the fiber volume to 0. This includes in particular the volume of the resolution curves. And therefore, in the F-theory limit, we recover the singular geometry which describes in F-theory the non-abelian gauge algebra of particular ADE type or generalizations thereof. And all of this can be made very explicit, though we didn't have time to discuss all of this in class, but it's in the notes. The simplest example is probably an SU2 Tate model. This is related to the Weierstrass model by completing squares and cubes. You can do this as an exercise and find this relation between these parameters AI and F and G of the Weierstrass model. There is an algorithm for how to implement the suitable vanishing orders at the level of Fg and delta in such a way as to recover the Kodaira fibers. For SU2 at W equals 0, this gives, following the algorithm which I reference in the notes, this pattern. A3, A2, A4, and A6 must factorize in this way. And then, as it turns out, the discriminant factorizes into two components, along one of which we have a double 0. Over this component, we have indeed an SU2 or I2 Kodaira type fiber, which we can resolve in this way, as done in the notes. And the remaining discriminant component, there we have a single vanishing order, so this would just be an I1 fiber. Questions about what we discussed last time? And if you want to know more about the resolutions, come talk to me later. We can go through it based on the notes or in other contexts, if you're interested. So now that we've established the origin of gauge symmetry, non-abelian gauge symmetry, what about matter and interactions, as Miriam already announced? So for the matter, we need to look at the codimension 2 behavior of the fibration. So we have that the discriminant in general will now factorize into various components, as we said, delta I, and each I has a gauge algebra GI. As we see already in this picture, inevitably there will now be codimension 2 loci on the base where two of those discriminant components intersect. This is an inevitable situation as long as the base has dimension, complex dimension 2 or higher. So in codimension 2, on Bn, n bigger equal 2, we can have, or we have, intersections Cij equals delta I cap delta j. This includes the case I equal j, in which case we would have a self-intersection. That would also be possible. So these are precisely those loci here. This one, this one, this one, or possibly also self-intersection. And over these, the vanishing orders of fg and delta increase. For example, for this SU2 Tate model, one can convince oneself by inspection of the following pattern. For the SU2 model, the simplest, we had this delta equals omega w squared times now an I1 locus, which was A1 to the 4 times a coordinate t plus order w, where t was a complicated expression, minus a1, a31, a41, minus a41 squared plus a1 squared, a62. This comes out by computation. So I encourage you to do this. Write your little Mathematica notebook where you plug all of this in and go through the list in this Kodaira table in the references. This is really great fun to convince oneself of all these vanishing orders. So we have here our base. Just repeating the picture. And now we see that this component delta equals 0, w equals 0, and here the remaining component, which is everything in brackets, will intersect in two distinct loci. Namely, if I set w to 0, then I have intersection w equals 0 and a1 equals 0, or w equals 0 and t equals 0, which is this polynomial. So this corresponds to these two loci, which we call Ca and Cb. So Ca, this is the locus w0 and a1 equals 0, the first one. And now you need to plug everything into f and g, and analyze the vanishing orders at this locus, and do this as an exercise in Mathematica. For this, however, you will need the higher order terms. So you can do this in Mathematica by yourselves. And you will find that here we have a vanishing order of vanishing of fg delta equals to 1, 2, 3. From what you see at the blackboard, it looks like it's different, but this is the answer, because there will be cancellations with these terms here, and this is what you will find. And there's a second locus, w equals 0, and this complicated locus, t equals 0. And there we have vanishing orders, fg delta, which is the intuitive one, 0, 0, 3. Also this you will find. Because here there will be no cancellations, because t as such will not appear in that form again in order w, contrary to a1. So that's why the behavior is slightly different. So what happens is that over those loci, in the singular model, the singularity type increases. So this here, for example, looks like a singularity of I3 as opposed to of I2 type, as we have over w equals 0 over generic points. And this is a type 3, Roman 3 Kodaira type. So this is Kodaira type 3, at least the naive one, and this is Kodaira type I3. This as such is not relevant at the end of the day. What is relevant at the end of the day is what happens in the resolution in the fiber. And what happens is that in the resolution y hat m plus 1, the fiber structure changes. Over those loci. And the rule of thumb is that to first approximation, the fiber type will be the fiber type associated with these naive Kodaira types which we get in codimension 2. But this is only a rule of thumb because the Kodaira type classification is really valid in codimension 1. In codimension 2 there can be monodromy effects which may delete some of the nodes of the affine Dynkin diagram. As you go around this locus, there will be some P1s will be exchanged and identified with each other. And at the end of the day, this will change the structure of the fibration over this locus, which is the fixed point locus of the monodromy. So the rule of thumb to first approximation is that the fibers in codimension 2 correspond to, again, the extended Dynkins of the enhanced Kodaira type but monodromy effects can delete individual P1s or individual nodes in that diagram. So I'm just saying, if you do the resolution, you will see explicitly what you have, and if it's not exactly Kodaira type, then it will be something that looks, if it's not exactly an extended Dynkin diagram, then it's an extended Dynkin diagram with a few nodes deleted. So in the SE2 example, one finds the following structure. Let's first look at the CA enhancement. So this is the fiber away from CA on delta, and this is the fiber over CA. So away from CA, but over W equals 0, I should say. We have the SE2 fiber, the I2 fiber, and I draw it now in Kodaira type notation, which is the same as this Dynkin diagram notation as we discussed. So we have here this P1, 0, and here we have P1, 1, which is not intersected by the section. And what happens, you can look at these, you can compute these two intersection points in the fiber. This is done in the nodes. And you will find that the intersection points of P10 and P11 in the fiber are described by the locus y times y plus a1 equals 0. I've set a few coordinates to 1 in agreement with the scaling relation, so that's why the scaling here does not quite work out, but up to this, that's the relation. So we see that we have a point y equal to 0 and a point y equals to a1. So this would, for example, be the intersection point y equals 0. This would be the intersection point y equals minus a1. And now it's clear what happens as we go to CA. We set a1 equal to 0. So those two intersection points come together and form a double intersection point. So over CA, the fiber looks like this. This is P10. This is P11. Those 2 points now form a double point. Which is precisely the Kodaira type 3. as expected, naively. So and this game one can play in all the cases. Once you have the resolution, you can simply go to all of those loci explicitly and do this game. And again, I invite you to do this in a few examples because it's fun and it's very explicit. What about the CB enhancement? So again, away from CB, we have, of course, the same fiber, P10, P11. And here something different happens. So this is computationally a little bit more complicated. You have to, because this locus is the locus t equals 0, so you have to find a good way how to analyze this. You can again do this in Mathematica for some purposes at least. You can do this, plug in that locus into the fiber, to the form of the fiber, and what you find is that okay, I should, well, just so I don't get confused, my notes now. Let me draw it like this. What you find is that one of the two P1s, namely this one, not intersected by the fiber, by the section, splits into two. So P10 stays, but this P11 will now split. So this is described by some complicated equation, and as we go to that locus t equals 0, that equation factorizes into 2, and therefore describes two disjoint rational curves, as you can check. So this would be P11 plus, say, this would be P11 minus. So I2 enhances precisely to I3. Could I write type I3 if you go back to this list from last time? And again, you see it by writing down the polynomial describing P11 and observing that as t goes to 0, it factorizes into two polynomials corresponding to this geometric factorization of the irreducible curve P11 into two irreducible curves, P11 plus and minus. The equations are in the notes. So we see a pattern. Okay, questions about this so far? Yes?
What's the difference between
None, sorry. Anything else illegible? Okay. So what happens here in type CB is the generic behavior. CA is an exception. The generic behavior is, as we see, that some of the P1s in the fiber split over those codimension 2 loci. So in other words, the components, the number of components of the fiber enhances. Here the fiber is 2-component, there it's 3-component. And one can write this as follows. The cone of effective curves, effective, which is for us holomorphic, essentially, curves enhances in codimension 2. This happens, this is true generically. CA is an exception. In CA, all that happens is that the intersection points degenerate, but this is the much more frequent behavior. In fact, this is what usually happens, that one or several of those curves will split as we approach that special locus. And this now makes it clear why these codimension 2 loci have something to do with matter, because we said all the matter states come either from C3 or from M2 branes, which can be wrapped on P1s. To the divisors, nothing really happens over this locus, but what does happen is that we get new curves, namely this curve and that curve. And M2 brane wrapping those new components, which exist only in codimension 2, give rise to new particles, which are confined to this codimension 2 locus, and as we will show, transform in particular representations different from the adjoint of the algebra. So M2 branes wrapping the new fibril curves give rise to matter in some representation R of the gauge algebras, the total gauge algebra, localized in codimension 2. Okay, I wanted to turn it down a bit, but never mind. What we need to understand the statement quantitatively is we need to recall how a representation of an algebra is actually defined in terms of its weight vectors. And for this, let's make a little group theory insert number 2. Thank you. Namely, let's look at Lie algebra G with a representation R. So a representation R is specified, as we said, by its weight vector, beta AR, for A goes to 1 up to the dimension of the representation R, the so-called weight vector. For example, in SUN, the fundamental representation is n-dimensional. So there are n states in the fundamental representations. And each of those n states has associated with it one beta I, or beta A, the weight vector. So each of those beta A is by itself a vector which contains in it the charges of that state under the Cartan U1 generators, such that the Cartan generators, these co-roots, Ti, acting on the state beta AR equals beta AIR times the state. Okay, so the weight vector contains for each state of the dim R many states in that representation, contains the charges under the Cartan U1s. So these are the charges under the Cartan U1I. And more precisely, we recall that to specify representation, it suffices to specify its highest weight. All the other weights are then determined by this, from this highest weight by adding to it suitable linear combinations of roots. So each representation R is specified by a highest weight, let's call it beta 1R, such that all the other weights, beta AR, are given by the sum of this beta 1R, this highest weight, plus suitable linear combinations of the roots. Where the alpha I are the simple roots. And the NA are to be determined. These depend on the representation. This is true for some, for suitable NAI. So for example, for gauge algebra SUN, the fundamental representation is the n-dimensional representation. Let's maybe call it, yes, that's okay, yes. Well, maybe let's call it capital N so we don't get confused. And the highest weight is given by charges 1, 0, 0 under, how many entries do we have altogether in here? N minus 1, excellent, the rank of SUN. And then beta 2 of R, that's beta 1 of R minus alpha 1. That's minus 1, 1, 0, and so on and so forth. Then you get beta 3 equals beta 2 minus alpha 2 in this case, and so on, until you arrive at 0 minus 1. That's then beta capital N. So in this case, you only add all the possible roots. And in other representations, it's different combinations of roots you need to add. All of this, of course, you find in Slansky. Or in the Lee art package, or whatever. OK, great. So this means that all we need to do now is we need to determine what the charges of these individual new curves here are, what the weights associated with these new curves are. How do we get this? What do we have to do in order to determine which representation would be a state from an M2 brane wrapping this new curve? What would be the recipe? Exactly. With what? Yes, with? That's right. Not with the zero section would give rise to the charge of the U1 KK. We want the charge of the Cartan generators, and these are these resolution divisors EI. Right? So the TI correspond to our resolution divisors. So we need to get the intersection numbers of the resolution divisors now with these new split curves, in exactly the same way as we did it for the fibers in codimension 1 in order to determine the roots. So back to geometry. Let's consider now this so-called relative Mori cone, the cone of holomorphic effective curves, which do not intersect the zero section. We want to not get the states that have KK charge. So consider the so-called relative Mori cone in the fiber over Cij in codimension 2. So this is the cone of all effective, i.e. holomorphic, curves in the fiber pi minus 1 of Cij, not intersected by the zero section F0. Again, because these correspond then to KK states, we want to now focus on the KK0 modes in going from F to M theory. So this cone is generated by, first of all those P1s which do not split as we go to a particular locus, and then the split ones. So in this example is so simple that here all the P1s which do not intersect the zero section split. There is only one and it splits, but in general you could have situations where some of them remain unchanged and only a few split. So the generators correspond to, first, all P1I which do not split over Cij, the ones that we have everywhere, and of course those which do split. These are the new interesting ones. All split curves over Cij, and let's call them C split, just to determine them. Give them a name. And then, indeed, we expect that, so the intersection number of the EI with the P1I, the ones that live everywhere, these will just give us the roots back. What's interesting is what happens with those split curves, and it turns out that the intersection numbers with the resolution devices EI, i.e. the charges under the U1I, Cartan, are precisely certain weights of a certain representation. So one finds in all the examples that EII intersected with the split curves. Again, this is a divisor, this is a curve, they intersect at points. That intersection number is indeed related to some weight of a representation. This is given by beta for some A, some weight times a sign epsilon, which depends on C split, for some representation R, for some A equals 1 up to dim R, and this epsilon is either plus or minus 1. So for some choice of representation, some A determining this representation, and either this can be plus or minus this representation. Of course, you can, when you have something with a minus, you can just as well think of it as the conjugate representation. But fixing, I mean, if you, the complex conjugate of the fundamental, say, has minus the weights of the fundamental. So this is kind of a matter of definition how you want to label things there.
Just come from the codimension curves, right? The codimension 2 effects don't enhance the case group itself.
Absolutely. Absolutely, yes. And eventually the reason for this will be, I mean, to show this, one has to show that the M2 branes, these new M2 branes in codimension 2, that they give rise not to vectors, but only to chiral hypermultiplets, whatever. This has to be shown, but this is the case and is the reason for what you said. Did I already? No. Yeah. Okay, so just, I'm overcomplicating things a little bit on the first read, but so that you are able to read the original literature which I'm giving in the notes, I want to introduce that notation, because otherwise it might be a bit confusing. Maybe it's not confusing to you, in any event. So the notation is that we write this intersection number with a curve, and we label the curve C, first of all by its weight, and then by the sign epsilon, in the sense that this is epsilon beta AR. Okay, so this is the curve in the fiber associated with weight vector beta AR, such that this relation holds for epsilon either plus or minus 1. And again, depending on how you fix R versus R bar, this tells you if epsilon is plus or minus. Okay, and then we are done. Questions?
Sorry, I'm a little bit confused. So, you're intersecting these new P1s that we have in coordination 2 with the old P1s that we have.
No, I'm intersecting it with the divisors, EI, which are the vibration of the old P1s over the divisor, delta I. It's those P1I vibrations over delta I, right? So these are, so to speak, PII over delta. This is the codimension 1 data. This is delta I, is the locus in the base, and over this locus I look at the resolution P1. The vibration of the resolution P1 over this base gives me a divisor in the full, and that's what. So on Calabi-Yau two-folds, this is itself a curve. And there it's really curve with curve. On K, say on K3, okay, this doesn't happen here. But in general, one has to carefully distinguish between the divisors and the curves. Thank you. More questions? Yes? The split curves, so these are the ones, this is the result of the splitting of the original curves P1I. So here, for example, this P11 splits into two curves, P1 plus and P1 minus, and these two, I would say, are split curves. It's maybe not ideal notation. So this is the exact notation. So in that example, one will then associate those two curves, P1 plus, P1 minus, with those. And we'll do this in a second. Yeah? So a holomorphic curve, so a non-negative multiple of a holomorphic curve is still a holomorphic curve. You can add them up with non-negative multiples without making them anti-holomorphic. So they lie in a cone. Yeah, I should have said that maybe. Okay. So we have some of the weights. Now we want to make, of course, the full representation out of it. Otherwise, there would be something wrong with the gauge symmetry in the singular limit. And the full representation one then gets by adding all linear combinations, as one should, to the of the non-split P1I, which correspond to the roots. Then, by forming linear combinations with all the P1I over this locus, one can form the full representation This corresponds precisely to the step of adding the roots to the weights in order to make up the full representation. And the details of the geometry will tell you which linear combinations you can take, such as to get an irreducible, such as to get a suitable BPS state from this. So all the curved linear combinations which correspond to BPS states will then populate an entire representation R. That's the claim. So in other words, such that the result then will be that given a representation R, this is one we found, then for all states in that representation, for all A, there will exist a sign epsilon and a curve C epsilon beta AR. Holomorphic, that's crucial. So that is constraining satisfying precisely this relation star. So we can form holomorphic curves by adding the P1i, i.e. by adding roots. And then we have this annoying, so the reason for this sign is because I insist here on holomorphic curves. If I were happy with anti-holomorphic curves as well, I wouldn't have to care about the sign. A -1 would just transform a holomorphic to an anti-holomorphic curve. But if I insist on working with holomorphic curves, then I must allow for these intersection numbers not to give me beta A in some cases, but minus beta A. So what does this mean? Now, if we have an M2 brane wrapping C beta AR with a sign epsilon equals +1, then this corresponds to a state beta AR. This is just by definition so. Now suppose I have another curve C beta of BR where epsilon is -1, then an M2 brane wrapping this would give rise to a state in representation R bar. But I want to populate the entire R, so what I take instead is the anti-M2 brane. The anti-M2 brane wrapping C epsilon equals minus of beta BR. This then gives rise to the state beta BR. And this -1 here I cancel by the anti-M2 brane, because the anti-M2 brane has just minus the Chern-Simons action, so the two cancel again. And in this way, I get a full representation R on the basis of holomorphic curves only, by allowing for either M2 branes or anti-M2 branes. Reversing this, taking anti-M2 brane here and M2 brane there, I get a state in representation R bar. And indeed, I get both of these.
Does something special happen if the representation field?
Then these two curves are the same. We will see this now precisely in this example, in the SC2 example. Then one has to be awake in order to do the counting right and not to get confused. But then essentially these two curves will be the same. Let's go through the example. So SC2 example. So we have over CA, nothing is happening, right? Over CA, it's just these two intersection points coincide, but there are no split curves, so no matter over CA. So that's an exception. But over CB, we had this splitting. P11 goes to P11 plus and P11 minus. So we know that E1 dot P11 equals, what do you think would this be? E1 with P11. That's what happens over the entire divisor. Say again? -2. This is -2. Because this should be the diagonal entry of the Cartan matrix. This should be minus C11 SU2 Cartan. That was the intersection in codimension 1. But now we come to the +1, -1. Now we know that we have this splitting here. And it turns out, this is not true in general, but in this example, it turns out that these two curves are homologous. In general, that's not the case. Here, the curve class P1 plus equals the curve class P1 minus. You can see this check via equations. The equations are in the notes. You can see that they are just in the same class. So therefore, the intersection numbers of these two have to sum up to -2, so they are -1 each. More generally, you have to work a bit more to get those intersection numbers, but that is just a geometric thing that you have to do. So for SU2, the fundamental representation has beta A of the fundamental equals -1 + 1, according to this rule. +1 -1, sorry, the other way around. And we can now interpret so the C plus, this curve is -1, so we can interpret this as C of the fundamental with sign plus of weight number 2, and likewise here of weight number 1. So C plus beta 2 delta is P1 plus. So beta 2 is this one here. So this -1 is precisely that intersection number. It comes with a plus. And C minus beta 1 delta equals P1 minus. So beta 1 should be +1. We get intersection number -1, so we include this minus sign here. That would be a consistent interpretation. Or vice versa. Of course, we can relabel. And we note another thing. We note that C plus beta 1 delta, beta 2 delta, that this is P1 1 minus C minus beta 1 delta. This is because P1 plus P1 minus is P1 1. And this is minus alpha 1. And this fits with this general rule for how we get the full representation by adding the roots. We have a minus sign here because we have here a minus. So this way we get one full 2 representation. Questions? Exactly. Precisely. I'll come to the very good, yes. So absolutely, this would give rise to full n equal 2 hypermultiplet in 4D language or in 6D language. Exactly. Just before I come to this one, last entry, but that's an absolutely crucial point. So we get a new entry in our dictionary between the geometry and the physics, that namely the relative Mori cone in codimension 2 corresponds to the weight lattice, or in other words, various representations R of localized matter. So the curves in codimension 1 correspond to the roots. The curves in codimension 2 correspond to extra weights. And I give you a bunch of references in the notes where this was discussed first in the 90s, and then more recent results where, in particular, the structure of the relative Mori cone was discussed and set in one-to-one correspondence with properties of the Coulomb branch. And now, indeed, now we come to this important point. Given those curves, we can consider M2 branes or anti-M2 branes, wrapping C plus and C minus correspondingly. M2s and anti-M2s. Recall that you won't recall this, but the structure of the supersymmetry is such that both the M2 and the anti-M2 in the M theory will be BPS states. Wrapping all holomorphic C plus minus beta AR. We have to consider both signs, depending on what beta AR is, all holomorphic. Depending on which one is holomorphic, gives rise to states in representation R plus R bar localized over CR. CR being the curve in the base. And the volume, the mass of those is again proportional to the volume of the corresponding curve. So in the limit where all the resolution P1s go into 0, in particular also the split curves will go to 0 in codimension 2. In that limit, all the volumes go to 0. All curves C epsilon beta AR and their volumes go to 0. And we get massless states. In representation R plus R bar. And the counting, what exactly one gets. So now is the question, which type of states? Now we only know that we get states in some representation, but what type of states are these? The statement is these are not vectors. Of course, they cannot be vectors because this is not an adjoint. This would be a disaster if they were vectors. They are not. And it turns out that in compactifications to 6 dimensions, so that's F theory on Y3 to 6 dimensions, one finds that these codimension 2 loci are just points on the base. So that's just a set of points, codimension 2 on the base and B2. And over each point, we have a full hypermultiplet, 6D hypermultiplet, 6D n equal 1, 0, hypermultiplet in representation R, which corresponds in 4D language of a chiral multiplet in representation R and a chiral multiplet in representation R bar. So at this stage, non-chiral. So each point carries 1 6D n equals 1, 0 hyper in representation R, which corresponds to 1 4D n equal 1 in this counting chiral multiplet in R plus 1 4D n equals 1 chiral multiplet in representation R bar. And this is again this quantization of moduli space argument by Witten. (9603-150), page 1314, which here is justified to cite because it's at 60. Yes, please. There can be situations, as you know very well, where you have only one half hyper in the like E7 1/2 56. So then there will be identifications. Yeah. So there will be few exceptions where you get half hypers. And then if n equals 3, so this would be F theory in 4D. Here I will discuss the meta-multiplicities next time. And at the moment, in absence of flux, we have non-chiral matter. So we have a number of 4D n equal 1 chiral in representation R. This is given by a cohomology group CR square root K CR, and the number of 4D n equals 1 chiral in R bar is given by H1 CR square root K CR. Cohomology groups with values in the spin bundle. This is the spin bundle of CR, which is induced by the holomorphic embedding of CR into the full space. We'll discuss this in more detail next time, but the chiral index of those is 0, so these numbers are the same. A, B, and note A equals to B. So in order to get chiral matter, as is required in the standard model and in more interesting gauge theories in 4 dimensions, we need flux, gauge background, as will be discussed next time. So A not equal to B, i.e. chirality, requires flux. As will be discussed in the next lecture. Not here, no. So there is one unique spin bundle, which is the one induced by the holomorphic embedding, and the claim is that this is the one. And in general, as Jim points out, there are many different choices, but only one of them is the physically relevant. Yes. 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 You can do the same, because the I1 is also a 7 brane. Right? You have 2 divisors which intersect. The curve is an intersection. So it's obvious what to do if the curve is a complete intersection of 2 divisors, because then a junction is obvious. Yes. Yes, indeed. This doesn't matter. If the curve is a more complicated ideal, it's trickier to get the explicit form, but there is again one, which is the correct one, which is the, yeah. Okay. Questions? More questions? Yes?
So are we do we think that these codes to defects, do we think of them as sort of fine brains? Or like,
Intersections of 7 branes. Yeah, good point. That's maybe something I should have mentioned. Very good. So we should think of them as intersections of 7 branes, and in the dual to B language, these would correspond to the open strings which are confined at the, or I mean, physically forced to live at this intersection locus, indeed.
so in the 2B picture, is there a way to see the general representation?
Another excellent point I should have mentioned in the 2B. So that's actually something. It's so clear to, or yes. So I haven't really stressed this point, but it's an important point. In the 2B picture, the only gauge groups. Okay, very good. Thanks for reminding me of this. In the 2B limit, in the 2B picture, in perturbative models, the only gauge groups that you can get would be UN, SPN, and SON. These are the only possible gauge groups that you can get perturbatively. This involves orientifolding. And the only representations that you can get would be the adjoint, of course, but then these are not localized. Of the localized ones, you can get the fundamental, essentially, and then you can get the 2-index antisymmetric and the 2-index symmetric one. And the reason is that you have perturbative open strings starting and ending. So an open string has only 2 points, one starting, one end point. That's why all the representations can be at most 2-index antisymmetric or symmetric. So this would, in fact, more precisely, this would be a fundamental under one gauge group and a fundamental under the other gauge groups. So you would always have one Champatten factors for each end. And if you have self-identification due to orientifolds, you get these guys. The use, there was the question, why is F-theory more interesting than just type 2B? The point is that we go beyond this purely perturbative set of branes, and we allow for now general gauge groups. G can be of general type, any simple gauge algebra. I'm only discussing the simple ones now. Of course, there can also be U1 factors. U1s on Friday in Miriam's lecture. The simple ones are the ones we have discussed. So in particular, exceptional F2, F4, and G2 groups which are not possible perturbatively, and much more complicated representations. So this includes those, but goes far beyond this. For example, for SO gauge groups, you can also have spinor representations, and then also, of course, representations under the exceptionals. And the reason is that what F-theory describes, done perturbatively, are general brane setups involving non-mutually local PQ-type branes, together with mutually non-local PQ-type strings between them. These are multi-pronged strings, which can have several endpoints and give rise to much more complicated representations. And this can be either read off by this dual M theory, or you can try and read it off directly in the 7-brane language. This is something that Oliver knows very well about, and the two pictures match. More complicated reps due to PQ 7-branes and PQ strings, which are multi-pronged. So developing this would be a lecture series by itself, and I apologize for not being able to cover this. But indeed, the upshot is that we are much more general. And that was kind of also the motivation. And this has important consequences both in model building. For example, in gut models or others, one needs other gauge groups, gut groups, say SO10 or spin10 gauge groups, but also other representations than the spinor representation. And of course, also when it comes to modeling or quantum field theories in general, this is a much more general set. Please.
So I remember getting by doing non-geometric
Okay.
asymmetric orbitals.
Very good, yes, very good. Yes. Geometric, yes, that's right. Thank you. Very good. And of course, perturbative in the heterotic dual, of course, one gets all of this also perturbatively, but not in the perturbative, let's put it this way, perturbative geometric. So perturbative geometric brain language. Thank you.
Do all representation show up, or there is some forbidden representation?
That's a good question. To my knowledge, it's not entirely classified yet which representations appear. There are people are working on this. There was a paper yesterday, for example, where so it's to my knowledge, it's not completely classified how high it can get, but it can get pretty high and pretty intricate.
That's sort of disappointing. Higher index representation.
But it's not classified. Is it classified? It's
They have some
yeah,
understanding of
yeah.
high index representation for SUN.
Mm-hmm.
So just one comment about that. So in Oliver's work, they showed that you can get arbitrary representations in principle, but the question from a mathematical point of view is in a concrete geometry, concrete compact
Right.
geometry, setting, can you get? And
Right.
there do seem to be some limitations where you cannot get in compact models arbitrary representations,
Right.
which can have questions associated, for example, with the model.
Mm-hmm. Exactly. Exactly. So the physics in codimension 1 is classified as far as the mathematics is concerned, but the physics in codimension 2, let alone now in codimension 3, is not yet classified. Not the physics, the mathematics, the geometry, I mean, the geometry. Okay, and a further point, I'm just saying it in words now. When we have singularities of the Kodaira type, then it is guaranteed that in codimension 1, by assumption, by this Kodaira assumption, we can have a flat Calabi-Yau resolution. But this does not mean that also in codimension 2, all the singularities that appear in such models can be resolved. So there are situations where in codimension 2, a Calabi-Yau resolution does not exist. And in that case, one has to work harder to interpret the model. Either one has to do certain blow-ups in the base first. This will then give rise to new states, for example, tensionless strings in 6 dimensions. But also after doing this, it might happen that we end up with certain singularities which cannot be taken care of. These would be Q factorial terminal singularities, so non-Crepant, non-Calabi-Yau resolvable singularities. And the interpretation in those cases is that one gets localized matter which is uncharged under any Cartan U1, meaning that it's not possible to give them a mass by going along the Coulomb branch. And I give you some references also in the notes. Okay, so this was matter. Now, very briefly, I won't need more than the 5 minutes, which I have. What about interactions? Matter, of course, is good, but we need to know interactions. And these are associated now with codimension 3 singularities. Sorry. So codimension 3 singularities can occur beginning with Calabi-Yau fourfolds, where the base is a threefold. So let's specialize to a fourfold, Calabi-Yau fourfold. So F theory in R13 times the Calabi-Yau fourfold. So suppose we have certain matter fields, psi n, which are localized in codimension 2 in various representations, n equals 1, 2, 3, 3 of them associated with representation Rn. What we're interested in is what types of couplings exist between those, like the standard model couplings or these dangerous couplings which would lead to dimension 5 proton decay, or dimension 4, or already also there can also be dimension 4 proton decay operators. How can we see if they are there? So necessary for the existence of a Yukawa coupling, and let's look at the renormalizable couplings here. For a Yukawa coupling psi 1, psi 2, psi 3 at the renormalizable level, is that, of course, these representations must allow for a gauge invariant contraction. So there must exist a gauge invariant contraction R1, R2, R3. It must be possible by looking at the tensor product of these three representations to get a singlet out of them. And this is equivalent to the statement that there exist combinations of weights of those three representations which sum up to 0, meaning that there are combinations of states whose total charge under all the U1 symmetries, the Cartan U1 symmetries, vanishes. So for all beta A of R1, say, there exists some, let's call this beta A1 of R1, there exists beta A2 of R2, and beta A3 of R3, such that their sum is 0. Meaning that the sum of the states, the sum of the charges of the states under the Cartans vanishes. Now, with what we know, this can be directly translated into geometric criterion, because we know beta AI Ri under, okay, this is now bad notation. Beta AR, I, is just given by the intersection number of the curve CR epsilon times epsilon an intersection number in cohomology. So if those intersection numbers are 0 for all U1I, this means that the curve must be 0 in homology. Or more precisely, this linear combination of curves must be 0 in homology. So sum I equal 1 up to 3. Epsilon I, n equal 1 up to 3. Epsilon n, C epsilon n, beta an Rn. This must be 0 in homology, so in H2 downstairs, hat Y4. This is a homological condition on those curves. This is a necessary condition, meaning that group theoretically we can form a contraction. This is necessary. In order to see if we really have such an interaction, this must hold not only in the cohomology of the fourfold, but it must hold over a particular point in the fiber. So there must exist one point where in the cohomology of that fiber we have this relation, meaning that we have really a splitting and joining of the corresponding M2 branes, realizing that triple coupling. So for an actual interaction, need this satisfied to be satisfied in the cohomology of the fiber over some point for some point P. So what we need is a situation that we have here 3 curves in the base. Some of these curves can be the same curve, so do not have to be 3 different curves. But they intersect now in a point. This is now a point, such that over this point, I'm bad at drawing, I apologize, but we have a situation where we have, so this is supposed to be saying that there is a curve class. This entire thing would be the curve class, say, C1, and this would be C2 and C3. 3 P1s, which correspond to the matter P1s associated with those representations, and they must join into, say, these 2 must join into 1/3 P1 given by this other state. So this would correspond to a joining and splitting of M2 branes. So it's literally, maybe I should draw it more like this, literally a picture of that sort, but not for perturbative strings, but rather for M2 branes wrapping P1s, and all of this must happen in such a collapsed panned over a point. So this is joining and splitting. Of the M2s, realizing the state psi n. Yes?
Does this correspond to like a node force condition?
It corresponds to in type 2b. Well, it's a condition that that we can form a linear that the boundary operators can be multiplied to the identity, essentially. You go from A to B, then from B to C, and then back from C to A. That would be exactly that condition that you can in open string language. So, in other words, let me conclude by saying that in order to study now these interactions, we have to study the codimension 3 structure of the fibration. This works in exactly the same way in principle as in codimension 2, so one has to specialize further and look at how various splittings occur. This is precisely such a splitting, but now for one of these P1s which are already localized over curves, just 1 codimension higher. And in this way, one can then classify the possible interactions in a model. And in particular, in general, it can happen that there exists an interaction which would be allowed by gauge invariance, but in that particular model, there is no point over which such a splitting exists. In that case, one would have an extra selection rule, for example, a massive U1, which would constrain the couplings even further. And this is something that can be explicitly analyzed. OK, thank you. Yes, please. Absolutely. So these are convex verifications to 2 dimensions. Then we get 2D 0,2 theories. And then in addition to this, you get codimension 4 singularities, which then give rise to a quartic interaction, which is allowed in 2D 0,2 because of the different scaling dimensions at the renormalizable level, quote unquote. Yes. So there is one extra layer then on a Calabi 5-fold. Indeed. Yes, there are. I wanted to maybe discuss a bit in the last lecture, but probably we won't. So, yes, this has been studied in the past. Yeah.
So these Yukawa interactions, they show up in the 4D effective action?
That's right. Absolutely. These would be Yukawas. So these would be renormalizable Yukawas of the type we needed in the standard model, or in, I mean, we are here in a SUSY context, in the MSSM, or in MSSM, in SUSY GUTS, or whatever 4D n=1 field theory you engineer in this way.
Okay. And then the gauge interaction just come because we engineered this thing so that all the matter already looks gauge.
Right. So this is the gauge interactions already appear, yeah, in the high, already in codimension 2, essentially, precisely. Maybe if there's no question, maybe if you allow me one more comment. So what has been done in the past in great detail is to compute the family structure, for example, of those couplings in local models. We learned yesterday that these family structures are an important thing in, for example, in BSM or in standard model applications. it is very difficult to do those computations directly in this M-theory picture. What the M-theory gives you at the moment is really which couplings could be there. But then in order to make these computations explicit and get the actual functional dependence of these Yukawa couplings on the moduli, etc., people have looked at effective field theory models, local models, where they explicitly compute the overlap of the wave functions localized at these intersection points. And the good thing is that since these interactions are localized at points, this requires knowledge only of the local geometry in the vibration, not necessarily of everything. And I guess something for the future would be to bring these two pictures better together and embed these very impressive local computations into such global contexts.
Tom, would you make, you announce? Yeah, say it now.